is titled as Maskless and Targeted Creation of Arrays of Color Centers in Diamond using Focused Animation Technology. And group members includes me and Priya. So the outline of my presentation is as follows. I'm going to talk about the introduction, that means what is the abstract of this paper, the applications of the focused ion beam technology, the experimental setup that we are going to use for this technology, the results in discussion and the references. So this paper, these are the authors of this paper. The abstract is as follows. So in this paper, we are going to demonstrate a method in which we are going to use the focused ion beam technology to generate the NV centers, most precisely the single NV centers. And this technology offers us resolution of around 100 nanometers, and hence it enables us to target the creation of single defects in diamonds. And this technology is totally maskless. That means we do not need any mask to make the NV centers, and hence it is ideal for to generate optical centers in photonic crystals or maybe some cavities, quantum cavities or diamond tips for scanning magnetometry. So as almost everybody has explained what are NV centers, so I'm not going into that. So in short, that they have unique quantum properties, and they are just nitrogen vacancy defects that we bombard nitrogen in the carbon sheet, and then we get the NV centers, and they are used in quantum computing and sensing. So the applications of using FIB technology to create single NV centers are as follows. There are some other technologies using which we create NV centers like AFM, and using in AFM we incorporate the mask. What is mask? So basically we have a sheet in which we make simple holes, and these holes guides us that where we need to generate NV centers. So, but here we do not need any mask technology. Masks are generated using electron lithography. So, without using any mask, we simply use a big ion beam, and then we focus it wherever we want to generate the NV centers. So, the applications are we can generate them in photonic crystals, tips and pillars, single photon LEDs, on-chip circuits, and mechanical resonators. The specialty here is that if you have a tip-like structure, maybe a diamond tip or maybe a pillar, on that tip it is very difficult to use a mask to generate the NV centers. But here, if you are good, you don't need any mask. So that's why these are very good applications. And as I already mentioned, that there is one another technology using which we generate NV centers, that is atomic force microscopy, in which we use AFM, and which has a sharp tip, and we simply scan the AFM on the whole surface, and below that we place a mask, and that mask has several holes, and those holes are precisely formed using the electron beam lithography. And obviously, since we need a mask, so maybe when making the mask, if there is some error, so that error will also propagated in the system. So to reduce those kind of errors, we are demonstrating a new technology which is totally maskless. That goes as focused ion beam technology. So in this technology, what do we use? We simply use a broad ion beam which is generated using ECR, that goes as electron cyclotron resonance plasma source, and then we focus the whole beam into a very small spot size using an objective lens, and the plus point is that it provides resolution of around 100 nanometer, and it offers maskless targeted ion implantation. And again, to see whether when we are scanning this, the small spot size, this beam, when we scan it, we also need to visualize whether wherever we are scanning, is it good, and is it the exact place, exact location where we want to scan it. So to do that, we incorporate this technology with SEM, electron microscopy as well. So this is the experimental setup for the FIB technology setup. So here we have this diamond sample, and in this diamond sample, we have two beam configuration. This one is the focused nitrogen ion beam, that is where we are bombarding the nitrogen atoms on this sample to generate the NV center. And the another one is to visualize and image the sample and guide for the fine positioning of where to check where the beam is working. So this is the scanning electron beam. And this is the whole setup above this, where we have this ECR plasma source. And this source, what is the task of the source? It generates the broad nitrogen ion beam, and then we take this beam from here, and then we use a lens system, condenser lens, blanking to maybe on or off the beam whenever we require. And this is a scanning setup where maybe we use motors to do the automation and all other things. And then again finally we use an objective lens to focus the beam, and the spot size is like around 100 nanometer or something. And this is a nitrogen gas cylinder that we have connected to this setup. So this is the experimental procedure. So we are using a nitrogen ion beam which is focused using the lens, and that's why we call it the FIB, and it is installed on an scanning electron microscope. And we are using the sample which is ultra pure CVD with a thickness of 200 micrometer, which is grown on a HPT substrate. And we demonstrated several arrays of focused nitrogen spots with dimensions of 21 by 21 with 2 micrometer separation each, that I am going to show in the results slide. The electron beam that we are using in the SEM, they are helping us, they are allowing us for the fine positioning and pre-selection. The main ion species that we are using in this ion beam, they are mostly N2 plus and some few percent of N plus as well. The depth of the nitrogen vacancies that we are creating, they are going till the range of nearly 20 nanometer. And also in all this process, after forming the NV centers, we also need to do the annealing. And during the process of annealing, it is possible to get some contamination in the sample. So in order to remove the contamination, the sample was cleaned in boiling acid mixture for like 4 hours. So these are the results. So as I told that we simply use the focus beam, and we on and off it to move it in the whole surface, and then we scan it, and we keep on making different spots with a dwell time of something like that goes as 500 microseconds to 1000 microseconds. And this is the zoom, this inset is a zoom version of this image where we have these 9 spots. And we are also characterizing this using the zero phonon line, where this is the NV minus and this is the intensity versus wavelength curve. Again, all the arrays that were designed, we designed them in the form of a grid, and with the where we have implanted N ions in each unit. For a single NV, we are measuring a width of around 250 nanometer, which is in agreement with the optical diffraction limited resolution. And we have also seen a relatively high and unwished density of NV centers having an area of around 1 to 5 micrometer per micrometer square at the diamond surface. This is due to the fact that because we are not using any mask filter on the FIB column. What is mask filter? It's like we can incorporate this setup with another Wien filter that filters the particles on the basis of their velocity, where we use the E cross B and velocity formalism to check, and it will just filter out the particles which has high velocity. And by convolving the measured implanted spot, it is found that the ion beam focus is having an average of 90 plus minus 20 nanometer. So again, apart from the zero phonon line characterization and this characterization, another analysis has been done, where we are, this one is using the confocal microscope. We are focusing to check the images, and we are analyzing the intensity patterns to count the NV centers. Another analysis we did using the ground state depletion imaging. In this kind of imaging, what we are doing, we are using 2 beams. One beam is being used to excite this whole sample, and after excitation, the whole sample will glow. But then again, we are using another beam, and using that beam, we are using a vortex phase mask. That phase mask is generating a hole in the center of the beam, and that second beam is going to de-excite the whole sample. But since there is a hole inside that beam, so this part will not be excited, and the rest part will be de-excited, and hence we will only see the NV centers glowing up, and hence we can count the NV centers. So this is how the characterization has been done. Thank you. References.
Keeping time and presentation. Questions?
Yeah, so in AFM also we have a like atom delivery system like that we can use on the tip of that AFM. So using that tip of the AFM setup, we can deliver the nitrogen atoms, and again there will be no precise control when we deliver that. So to do that we use a predefined mask, a mask that is generated using electron beam lithography, and using that we deliver the nitrogen atoms to wherever we require them. It's sort of like we bombard them using that like high field, like FM has I think high field, high electric field, so using that.
No, but this is not the purpose. It was a little bit different. That was actually where they were using in the experiment. They were using an L15, a very specific. It's a pyramidal shape, rather stiff like that. So it's a small angle, and then using a feed machine, they drill a very tiny hole inside the film.
What machine?
A focus ion beam.
Okay, fab machine.
They drill the hole, very tiny, something like 20 nanometers, and then you put the
You
AFM
place.
in the contact of your sample, and then or just a little bit above, and then you implant through this hole.
Okay.
And then the idea was that then you move, and then you do another implantation, then you move and you do another implantation. But the problem is that it's very hard to control the array. It was very hard to control the tip. It was also very hard to control where the hole was actually. So this was not a so reliable technique. But somehow it allowed higher resolution than the one that we had, which was something between 150 nanometer. And we tried actually after that to see whether or not we could have higher resolution, and this is a little bit difficult actually. It's not so easy to have higher resolution due to the fact that somehow if you come back to the skin of the machine, where there is the plasma source, you have a hole, and it's basically that hole that sets the resolution of the whole color. And if you now go to smaller hole, unfortunately, the plasma, you do not couple very efficiently the plasma out. So at one point, basically, 15 the resolution of that machine cannot go below 50 nanometer. That's the technique. But 50 nanometer is already quite nice, and you can also do